Hi, so my name's Nick, and this is my CS139 presentation on the arithmetical hierarchy. So, to review some of the sets that we've gone over for decidability in class, the three that we've gone over are decidable, computably enumerable, and co-computably enumerable. For a machine to be, or for a set to be decidable, that means that you have to have a Turing machine which will accept or reject on every input um, given from that set. A set is computably enumerable if there's a machine which will accept everything in that set, but is not guaranteed to reject the things that aren't in it and could loop as well. For a set to be co-CE, is said that the complement of that set is computably enumerable. So what the arithmetical hierarchy allows for is just a lot more classifications and actually an infinitely more classifications for sets to determine how decidable they actually are. On the right here, you see there is a sigma on the left side, a pi on the right side, and in between there's a delta. The sigmas kind of go up on the left the whole way, pi is up on the right, and the intersection between the two is where you would see the delta. The way that these are defined are like this, and these three definitions come from the Cozen textbook. Sigma 0n is the set where the quantifiers defining it alternate from uh, ex, existential, universal, existential, back and forth until you get to a quantifier q, which will depend on whether or not n is even or odd. So just how many quantifiers you're going to alternate between. Um, this is the way that sigma 0n is defined. Um, and pi 0n is defined in pretty much the same way, except for the fact that it starts with a universal quantifier instead of a existential quantifier. The delta 0n is defined to be sigma 0n intersected with pi 0n. The way that this works is that basically delta 0n is simply defined on if a set is sigma 0n and the set is pi 0n. The r that you're seeing at the end of these sets is a predicate. So all of those variables that are defined, such as exist y1 for all y2, exist y3, those all have to fit into this predicate in which that predicate needs to be decidable, which it'll be easier to understand in a second. Um, one way to understand the sets that we had before are now in terms of the arithmetical hierarchy. So sigma 01 is actually just the computably enumerable set. Pi 01 is the co-computably enumerable set, and delta 01 is decidable. So as you saw from before, the intersection between sigma 0n and pi 0n is delta 0n. And as we know, if a set is CE and co-CE, then it becomes decidable, and that's shown here as well. Now, the halting set, as we know, is computably enumerable. And we can write this set using the definitions from before for sigma 0n. We can show that the halting set is in sigma 01, which we know to be computably enumerable set. So H needs to then be defined in the way that we had shown before for sigma 0n. So we say that given an input, a machine M and X, there needs to exist a Y such that, and this is where the predicate comes in, where there needs to be a machine X that after Y time steps, that the machine will halt. We can build a Turing machine that will be able to decide this exact predicate. And that's an important part of this whole structure here. And so the way that we set this up then is we have a single exist y, which means that there's only, since it's starting with an exist and there's only one, that means since it starts with exist, we know it's going to be sigma. And because there's only one, that means that n is just a 1. So that's how we end up saying that h is a part of sigma 01. the complement of the halting set is not computably enumerable, as we know, because if it was, then that would make the halting set decidable. But before, we just knew that the complement of this set, which would be a machine that halts, or a machine that halts in every single input in a given set. And we weren't really sure where to place it because we didn't have a classification for this. But now we do, since we have the arithmetical hierarchy. So the halting set's complement can be defined as this. Given a machine, for all inputs x, there exists a time step t such that when you run x on this machine, it will halt after y time steps. This is pretty similar to the last way of defining h, except for the fact that instead of showing that it's just for a singular x, we want it for all x. And that's what changes this into actually the arithmetical hierarchy classification for pi 0, 2. We see that it starts with a universal, which means that we are going to need a part of the pi based off of the definition. And we see that it alternates 2 times, which means that it's going to be 0, 2. So we can now have a definition or classification for the set H, H's complement, which we weren't able to have before. One more definition that needs to be given to kind of help explain how the hierarchy actually holds together and explains what the differences between the sets are is the idea of a set being complete. So a set X is said to be complete for a set Y if X is in Y, and for all Z in Y, Z is able to reduce to X. So a way of describing this is using H as an example. H is, for example, complete for the set CE. So what this means is that first, H, meaning X here, needs to be a part of Y, which would be CE. So H is a part of CE, which we know that from before, that we proved in class. And so that's the first part of this definition of something being complete. The second part is saying that every single set that belongs to CE will be able to reduce to H. So it's basically saying that H, everything up below it is able to reduce to this. And it has to be, specifically, H needs to be in CE. So what ends up happening is H can then basically be one of these anchor points in what's kind of holding up the entire hierarchy at those points. If we didn't have these complete sets, then those points would be much more vague, and the whole hierarchy would become collapse if it doesn't actually work out. So, in conclusion, the arithmetical hierarchy is better for classification for a set's decidability because there's infinitely many different classifications, and you can just go higher up for basically if the set is more and more undecidable. The sets DEC, CE, and co-CE that we had defined in class aren't now not usable because we're able to basically set them to these new classifications instead for the arithmetical hierarchy called delta 01, sigma 01, and pi 01 respectively. And so, and the last thing that I went over was the fact that the hierarchy is held up together at those points because of those complete sets. Otherwise, it would be kind of vague and confusing as to how the hierarchy is actually set up. So that was my presentation. Thank you for listening. Bye.